And we have a distinguished speaker, Dr. Wilbus, with us. So this colloquium is, in honor of Dr. Ananthakrishna. We started it today, is 66th, and we have honorable speakers in all these sessions. So Dr. Wilbus required no introduction because we all listened to him yesterday, but still as a custom, we just introduce. So he's an associate professor at UC Berkeley and teaching at Department of Earth and Planetary Sciences. And he has a PhD received from MIT, and then he worked at Yale, and then now at UC Berkeley. So he extensively works in the field of tropical meteorology and atmospheric dynamics, and he has several colleagues who also from India. So that's one good thing that we remember about Dr. Will. And okay, so with this short introduction, I invite Dr. Wilbus to give that colloquium, and we will listen to it. Thank you.
Thank you. You. Hello, everyone. Thank you for being here. My plan is for this not to be an hour-long talk. I think I have something like 20 slides. I'm going to go through them a little systematically, but my intent is that we have some time for discussion, that this will be shorter than my talk yesterday. I'm talking to you about orographic precipitation, which I think is a very old problem. But what I'm going to argue is that orographic precipitation in the tropics, because it involves convective clouds, is very different and less well understood than orographic precipitation in the mid-latitudes, where it has been much more well studied. A few years ago, I saw a statistic, which is that roughly 40% of the human population, we have 8 billion people on Earth, so 40% of those 8 billion people actually get their water from orographic sources. So orographic precipitation is a huge problem. It's a very important phenomenon for human water resources and how they will change in the future. I want to emphasize that a lot of what I'm going to talk to you about today is the vast majority of what I'm going to talk to you about today is work that's been done by Quentin Nicholas, who was a PhD student in my group at UC Berkeley, and he just graduated 3 months ago. He's now on a little bit of a break before he starts a postdoc fellowship at ETH in Zurich. I wanted to begin, this is actually a prompt from his thesis, comparing a map that was made 140 years ago.
Yeah, maybe you can start the entry. Maybe the big time here.
Oh, thank you. It's very scratchy. Is this, maybe this is better?
Yeah, I think you're certainly
it was too close.
That way.
Okay.
Not bad.
Is that better?
Just for
Okay.
yeah. Yeah.
It's still, I think I'm still hearing a little bit better. I'll just try not to speak as much. All right, well, we'll give it a try. Can you hear me okay when I talk like this? It's okay. All right, please give me a, do you think we can do anything to improve
This might be
yeah.
handheld might be okay.
I thought would be fine, yeah. Okay. How's that? Is that better? Can you hear me well in the back? Yes? Okay, great. Thank you. All right. So they're not able to hear in the back. Okay, what about that? Is that good?
Hello.
Okay, so that's good? All right, great. So,
hello.
these are two different annual mean climatologies of rainfall over India. And I thought this was nice to begin with because, one, this is modern day spaceborne radar estimates of the annual mean precipitation. So this is not summer, this is annual mean. But this is a map made from rain gauge data 140 years ago from British geographer Trelawney Saunders in the year 1881. And you can see certainly we plotted these on the same color bar in inches per year, just for comparison. But the nice thing is that back 140 years ago, they had a pretty good estimate of how much rain was falling in these orographic precipitation maxima along the coasts of Myanmar and the Western Ghats and even parts of the Himalayas. Maybe they were a little too weak over the core monsoon zone, especially in this region. But you look at these maps, and my main point is that what really stands out are these orographic precipitation maxima. Here, here, and here. This core monsoon zone is a very important region. I talked yesterday about the storms that bring a lot of disasters, primarily to this region right here. But today I would like to focus on a general phenomenon that is relevant to these rainfall maxima right here along the edges of the orography. And I think this is important because when we talk about monsoon dynamics, we often think about a thermally forced circulation. And we think about the land surface, a non-elevated land surface, not heating the atmosphere, driving a large-scale monsoon. And we don't necessarily think about these narrow north-south oriented mountain ranges being, a key component of the monsoon. This holds up globally when you look at this is now the July climatology of precipitation. The South Asian region is split in half by this particular map projection. But you see from this GPM iMerge precipitation data set, the rainfall maxima in India and along the coast of Southeast Asia, a lot of the rainfall maxima in the maritime continent, Papua New Guinea, Borneo, then this region here over the very coastal region of Central America, South America, Western Africa. There are these maxima that look like they're strongly organized around orography. So this is an important problem globally. And I want to zoom in now on this South Asian region and show you winds overlaid on that precipitation distribution. So this is now the Northern Hemisphere summer precipitation. You can see these orographic maxima here in the map form. And if I plot a section of surface height along this magenta line right here, you can see in this season the wind is eastward, as you all know well in this room probably. We have the June, July, August mean precipitation shown here in the green contour, and you can see these orographic precipitation maxima. And one thing I would like to draw your attention to is, especially when you look at, for example, the Western Ghats, the length scale of the upstream rainfall enhancement is quite large. You see that rainfall is enhanced upstream of the Western Ghats by easily 1,000 kilometers. Is that purely because of the orography? Well, who knows, right? But it's suggestive that upstream of each of the orographic precipitation maxima, the rainfall falls off over a fairly large length scale. When we go to the opposite season, we now go to early winter or a very late fall, October, November, December. The winds reverse direction, they're a little bit weaker, but the rainfall maxima moves to the other side of the orography. So this is what you know here in India is the winter monsoon in Chennai, but we have the same thing happening over the coast of Vietnam and other orographic regions too. So I want to ask the question today of what sets the magnitude of these orographic precipitation peaks. You know, why does this peak in summer at 22 millimeters a day and not 30 or 10? And what sets the horizontal structure? What sets that length scale of the upstream enhancement? What sets the magnitude of the rain shadow? And what sets the length of the rain shadow? To do that, we're going to begin by talking about what existing theories are there, what existing concepts do we have for thinking about orographic precipitation. And we first need to divide orographic precipitation into two primary categories. One of them is what's called mechanically forced, which is a mean wind, some sort of background, strong horizontal flow hitting a mountain range and going up over the mountain range, assuming it's not deflected around it. And as air rises, the air parcels cool. Classically, we think of the entire layer of air that's ascending over the mountain cooling. Water vapor in that layer at some point will condense and fall out as rain. It's sort of a convectively stable problem, this classic problem. You can write an equation for the rain rate, here written as S in this 2005 review paper by Gerard Rowe, which is just the wind speed dotted with the horizontal gradient of the surface height. And then you multiply that by some vertical derivative of water vapor or the saturation specific humidity, assuming you've reached saturation. Another main type of orographic precipitation is thermally forced, where the orography is doing something thermodynamically to the atmosphere, meaning it's acting as a heat source. This is a very important type of orographic precipitation. I think this is something that probably in the Himalayan region plays a strong role, maybe not 100%, but a strong role. The Western Ghats seem to have a weak diurnal cycle. The mountains off the coast of Myanmar also have a weak diurnal cycle. We think they're more in this mechanically forced regime. Today, I'm only going to be talking about mechanically forced orographic precipitation. So existing theories for mechanically forced orographic precipitation are essentially what I just described was a simple, what is called an upslope flow model. So you say a condensation rate is equal to a vertical integral of the vertical advection of water vapor. So if you write down a full moisture budget, a full water vapor budget, you think of water molecules as being conserved, then their advection, if you integrate their advection vertically, that has to balance the net source or sink. If you think of the net source or sink being due to precipitation, that would be the sink. You say horizontal advection is quite weak compared to the vertical, and so to get the net precipitation rate, it's equal to the vertical integral of the vertical advection. To get vertical advection, you need a vertical motion, and the vertical motion is just what flows uphill, right? So you say, you take your horizontal wind, you dot it with the gradient of the surface height, and that gives you a vertical wind. You plug that in here, and then if you know your air density, just from density decaying exponentially with height, and if you know your temperature, you know your saturation humidity, and you can get a precipitation rate from this simple upslope flow model. And it looks like this. It gives you rainfall, shown in the green line. You get a strong rainfall peak on the windward slope, a rain shadow on the leeward slope. The colors here show the vertical motion. In this simplest model, the vertical motion is invariant in height. And outside of the mountain range, there's no upstream enhancement. The rain shadow does not extend downstream of the mountain slope. We can make this more complicated, and there has been a whole body of literature over the last 20, 25 years or so, which says, well, the vertical motion is not just simple upslope flow. It actually is comprised of a gravity wave that's excited by the flow over the mountain, an orographic gravity wave. These gravity waves, if you have flow over a mountain and the flow is not blocked and forced to go around the mountain, they have this tilted structure, and you have alternating upward motion is shown in red, downward motion is in blue. So the flow essentially goes up and then descends quite rapidly down. And you have these tilted bands of up and down motion, and your upslope or your windward precipitation peak will be substantially smaller than in that simple upslope model. And note that you then have a rain shadow that begins a tiny bit before the peak of the mountain, but the rain shadow ends very close to the end of the mountain, and the rainfall is enhanced a little bit downstream of the mountain because of that gravity wave response. So this is a body of theory that came by combining linear gravity wave dynamics with this sort of simple model for precipitation. Ron Smith at Yale, who was my colleague when I was at Yale, really created this whole effort before I arrived. But what we did is that in the past 5 or 6 years, we started looking at orographic precipitation in the tropics. And these are 2 overpasses of spaceborne radar, the GPM Doppler radar, the DPR radar, but this is the KU-PR radar from that GPM satellite. And we're showing you a pass over British Columbia to give an example of a classic mid-latitude precipitation regime, classic mid-latitude orographic precipitation regime. And what I want you to see here is that this is the map view of the radar reflectivity shown in colors. And when you get up to red, that's a lot of radar echo, a lot of condensate in the atmosphere, high rain rates. And this is a long track distance. So you're looking at a vertical section along this line. And this is altitude. And what you see is basically this system. This is your bright line. But you have roughly a whole layer of the atmosphere that's going up and over the mountain, and that whole layer is undergoing condensation. Fits well with that classic conceptual paradigm. But if you look at this Western Ghats orographic precipitation regime, it looks nothing at all like this. We are looking at a different geometry, but if you looked crosswise in the paper, we do have a crosswise section too, but I like this view better because it really shows you the degree to which along the topography you have all these little isolated convective cells reaching up nearly to the tropopause, 10 kilometers altitude, even though the Western Ghats are not that high of a mountain range, right? We're not talking about the Himalayas, the peak height, the mountain range height. We might think of it as being around a kilometer or so, maybe if we average over a pretty broad region, maybe even a little bit lower than that. And so the question is, if you have flow over a mountain that only reaches, the mountain height itself only reaches up to this level, how do you get condensation extending all the way up to nearly an order of magnitude higher than the mountain itself? And why don't you have layer-wise condensation? Why do you have this kind of ensemble of precipitating individual cumulus elements going off within that flow? So Dan Kirschbaum, who is another researcher who's done a lot of work on orographic precipitation, had this nice quote. He said, "The majority of past research on orographic precipitation has focused on the stratiform, the layer-wise mechanically forced type, which is a challenging problem in its own right. Less attention has been devoted to the more complex problem of convective precipitation, despite its importance." And so what we did is we proposed a new simple way of thinking about orographic precipitation.
What was during monsoon season, right side, India?
This is during Northern Hemisphere summer. Yes, this is a winter time. Right. Yeah, these are individual events, obviously. Yeah.
Average height of this British Columbia.
What is the what?
Average height of the mountain. Because Western Ghats is 1.2 kilometer.
You can see the mountain right here. See how the reflectivity, there's these gray regions where you don't see it. So you can see the Western Ghats right here, and you can see the mountains of British Columbia right here, this sort of gray area. So they're going up to, you know, easily 1.5, maybe even almost 2 kilometers. So we're going to proceed quite simply. The goal is not to, we're not producing a high resolution, realistic simulation of orographic precipitation. We want to say, what's a good way to think about conceptually the problem? So what we're going to do is we're going to take a very different approach from saying precipitation is equal to vertically integrated water vapor advection. We're going to say convective elements in the flow, or the ensemble of convective elements, respond to the thermodynamic perturbations produced by the mechanical forcing of orography. So we have a background wind hitting a mountain. There's some layer here shown in this pinkish color that is below the base of cumulus clouds. And that layer has a certain temperature and humidity that will represent the combination of those two variables as the equivalent potential temperature. You can think of this roughly as the energy or the entropy content of this subcloud layer. And we'll just think of a simple scenario where this is a constant, a horizontally uniform sea surface temperature. And the only land is this mountain right here. Uniform wind. The wind goes up the mountain on one side and then down on the other. When it goes up the mountain on this side, the vertical motion cools this part of the atmosphere and moistens it, because you have upward advection of humidity and adiabatic cooling. On this side, you're warming and drying. And then what we are thinking of as happening is that the convection responds to these free tropospheric anomalies of temperature and humidity. And we're going to borrow a closure that I liked, a simple closure in the past. One theoretical closure people have used often for convection is a Betz-Miller scheme that uses a free tropospheric temperature averaged from the boundary layer all the way up to the tropopause. We've found that orographic precipitation, convective precipitation in general in the tropics, seems to be highly sensitive to temperature and humidity anomalies in the lower free troposphere, not the boundary layer, but above the boundary layer in the lower free troposphere. And so this closure that was formulated by Fayaz Ahmed and David Nealon and co-authors, published in 2020, we're essentially borrowing this. And it says that precipitation anomalies are proportional to the humidity anomalies of the lower free troposphere. You could think of this as a layer extending maybe from 900 to around 600 or 700 hectopascal. They increase with the humidity of that layer. They decrease with the temperature of that layer as you become more stably stratified. And they also increase as the theta E of that subcloud layer increases. So these are your three variables that control the precipitation rate. And each of those there's a proportionality. Each of these has a time scale in the bottom that is observationally derived. And these time scales can vary from 3 hours to 12 or even 20 hours, longer time scales for the moisture adjustment. So we're going to go back then, we're going to combine that simple convective closure with the same sort of linear gravity wave theory that has been used often, that I outlined Ron Smith used for the mid-latitude precipitation. And from linear theory, you can actually get a vertical motion distribution for any given orographic shape. For certain topographic shapes, you can do it analytically. For an arbitrary shape, you can do this via Fourier transform because it's a linear theory. But for this mountain shape right here, this is the vertical displacement. It's if you have an air parcel moving like this, this is the contour. The colors here show upward displacement, and the blue shows upward displacement, the orange shows downward displacement. So air parcels move like this, they go up, and then they start to go down. And you have that tilted gravity wave structure. upward displacement will produce cool and moist anomalies. Downward displacement will produce warm and dry anomalies. So you'll have T prime negative upstream, Q prime positive. And remember that negative temperature anomalies in the free troposphere, positive humidity anomalies produce enhanced precipitation, and vice versa for warm and dry anomalies. So this, for this mountain shape, this is the analytical precipitation solution that you can get by combining that linear gravity wave theory with that simple convective closure that I outlined. And what you note is that you get a peak precipitation for a mountain of about 1 kilometer height, of exactly 1 kilometer peak height. Your peak precipitation is around 25 millimeters a day. And it has a pretty long upstream rainfall enhancement. Note that the rainfall, there's a background rain rate of around a few millimeters a day, maybe 4 or so millimeters a day. Takes a while to recover. But this would be your background radiative convective equilibrium precipitation rate up here. Your rainfall enhances easily 500 kilometers upstream of the mountain. So the rainfall peak, the orographic peak, is not just over the upwind slopes. The rain shadow extends well beyond the mountain itself, and you don't, unlike that classic mid-latitude theory, you don't have a peak downstream of the mountain. And the rain shadow is quite long. It's the region of 0 rainfall downstream is 300 to 400 kilometers downstream, and you're depressed below the background value for easily 500 or 600 kilometers. So again, the main ingredients of the theory are you take your background temperature, you put in temperature, humidity, and precipitation. You allow there to be an anomaly. You have those anomalies influence your precipitation via your convective closure. We take the anomalies and we divide them into 2 pieces. So the anomalies, we say there's going to be an anomaly that comes just from the adiabatic linear gravity wave response to the mountain. And then there's going to be a convective feedback because the precipitation, the convective clouds, influence the temperature and the humidity. However, we're going to make the simplifying assumption that the convection doesn't alter the temperature of the free troposphere. That's a big simplifying assumption, but it's consistent with what you might have heard of as the weak temperature gradient theory for the tropics, which says that horizontal temperature anomalies are very weak or negligible. And so if you know temperature in one part of the domain, like upstream, far upstream of the mountain, then within a deformation radius, which is very large in the tropics, you know the temperature everywhere within that distance. So that's why we're neglecting the convective feedback on the temperature anomalies, but we're preserving it on the moisture anomalies. Then those go into your convective closure. And what that allows you to do is it allows you to obtain a one-dimensional equation for the precipitation anomaly that you get from that orographic perturbation. And an interesting thing is that you can see from this sort of solution that you get a length scale, this L sub Q variable, which is equal to the background wind speed times that time scale for precipitation to respond to humidity divided by what's called a stability parameter that's called the normalized gross moist stability. Yeah.
So this simplification only you are getting temperature anomalies as negative upslope. You are not counting for latent heat, right?
We're not allowing latent heating to feed back on the temperature anomalies.
This is why you are getting negative temperature anomaly upslope, right? In the previous slide you were showing.
So on the previous slide, so the colors are vertical displacement. So you could think of this as, blue is cold and red is warm.
P prime is negative because of that assumption, right?
So I will hold that thought and we'll come back to that. Okay, I'm going to show you some cloud resolving model results. where we'll see how that simplifying assumption holds up. Okay, but the nice thing about having a closed analytical theory is that this normalized gross moist stability, I'm not going to go into details on this. If you're familiar with some tropical dynamics, then you might, this is basically the reduction of the traditional dry static stability by some moisture stratification. But you can see that as the wind speed increases, you expect the this length scale of over which precipitation will respond to increase as it takes longer for precipitation to get rid of a humidity anomaly. It'll also increase, and it's inversely proportional to that stability parameter. Okay, so that's the theory. What we're going to do now is see, does that work, right? Does this give us a way of thinking conceptually about tropical orographic precipitation? And we're going to take a cloud resolving model that's in a very long domain. It's like a very long bowling alley or a long tropical channel. We're running it in a domain that's 10,000 kilometers long. I'm showing you only less than half that domain. I'm showing you a little over -2,000 to +2,000 kilometers, centered on this 1 kilometer high mountain range. And this is the cloud resolving model with horizontal grid spacing of 3 kilometers. This model has an imposed background wind. So we're imposing a cross slope flow of 10 meters per second. And what you're seeing here is the vertical velocity. And so this is a moist convection permitting model. So water vapor is in this model. It's active, it can condense, it can precipitate, and yet we still see this classic nearly linear gravity wave structure showing up in this model, even though there's precipitation interacting with the flow. Zooming in on this region, on this -400 to +400 kilometer region centered around the mountain, and looking at the vertical motion around 500 hectopascal altitude, I'm showing you the vertical motion because I want to convince you that the precipitation is still convective. This is not layer-wise ascent. The vertical motion is concentrated in all these little updrafts, these little convective cores where you have ascent, some downdraft surrounding them. So you have convection upstream in the mountain, and when convection is over the mountain, it becomes a lot more active. And so just reminding you that the problem we're working on, the question we're asking is, how is an ensemble of cumulus clouds modified by the mechanical perturbation of the flow by the orography? When we compare precipitation from that cloud resolving model, this is the WRF model, the WRF model, it's the blue curve right here. The mountain is the mountain height is the gray curve. And our theory is this, the analytical theory is this magenta curve. And this is not a perfect match by any means, but for such a simple theory, I think, honestly, I'm happy if it's correct within an order of magnitude or a factor of 2. And I think it does come fairly close to getting the peak correct. It gets the length scale of the upstream enhancement. Note that in the WRF model, you have roughly 1,000 kilometers upstream in the mountain, rainfall is enhanced. Just like we saw in observations for the Western Ghats. Downstream of the mountain, for several hundred kilometers, there's 0 rain, and then rainfall is depressed below its background value, shown here in this horizontal line, for over 1,000 kilometers downstream of the mountain. And the theory captures that downstream reduction of rainfall quite well. When we compare that to the classic mid-latitude theory, the classic mid-latitude theory produces very little upstream enhancement, an extremely short rain shadow, and it gives you this spurious downstream rainfall peak, which doesn't show up in the cloud resolving model. So I think that having this theory is important because we often remember that orographic precipitation supplies water to 40% of the human population. Even when we turn to high resolution global climate models, by high resolution, I mean ones that are going down to quarter degree. This is 3 different slides showing 3 different climate models. As you enhance the resolution from 2.5 degree or 1 degree or even half a degree down to a quarter degree, or this one down to just half a degree. But one thing I'd like you to note is that there doesn't seem to be any systematic improvement in the orographic precipitation in these models. The ECMWF model kind of has good orographic precipitation maxima at both of these resolutions. All of these are compared to the iMerge data in black. In this MOHC model, the precipitation maxima simulated by the model are so strong that we had to use a different vertical axis. And you'll see as you go to finer resolution, the orographic precipitation maxima, which were too strong compared to reality, get actually just narrower and even higher, right? It's like the error just becomes higher resolution. And NCAR, you could maybe say it's doing something roughly right with the Western Ghats. This is India right here, and here's the mountains of Myanmar, but it doesn't get this Myanmar peak at all. So that's laying out the basic ideas for what we're proposing as one new way of potentially thinking about tropical orographic precipitation, at least the mechanically forced type. What I want to do now is say, well, what good does that do us, right? So there's a new theory for something. Does that get us anywhere practically? And what we're going to do is say, let's think about how orographic precipitation might change, especially as a function of the climate state. What happens if the Earth warms? How will orographic precipitation respond? We are working on that problem. It turns out to be a hard problem, and we don't have an answer yet. So what I'm going to show you instead is a different answer, which is how does orographic precipitation respond to changes in the wind speed as air flows across a mountain? If you have, say, imagine that the monsoon westerly jet, as it goes across the Western Ghats, strengthens or weakens by 1 meter per second over the next 100 years. How would you expect that rainfall peak over the Ghats to change? Well, we can turn to that theory, and we can just take that analytical theory with that linear gravity wave coupled with that convective closure and just say, how much does the precipitation peak respond? And the theory spits out an answer very quickly, and it's an increase of 25% of that precipitation maximum for each 1 meter per second increase in the cross slope flow. So 25% per meter per second. That is huge, right? I think that when we think about the monsoon circulation weakening, for example, you might imagine you double greenhouse gases, maybe you warm by a few degrees Kelvin, water vapor increases in the atmosphere at 7% per Kelvin. So you might imagine atmospheric water content increasing by 7% per Kelvin times 3 Kelvin, right? So that's 21%, call it, for simple numbers. 21% for a 3 Kelvin warming. Well, is it plausible that monsoon westerlies would weaken by a meter per second? That seems plausible, right? We don't know that it will, but it seems plausible. Would you then, would you get a 25% reduction in rain rate due to that weakening of the dynamics? That's what the theory tells us. Why does the theory predict such a high sensitivity, right? Because we have a theory, we can take it apart and answer that question quite easily. Well, it's because we have this precipitation closure. Remember, precipitation is sensitive to temperature and humidity anomalies averaged over some lower free tropospheric layer, shown here as this box right here. this is height. Here's the temperature anomaly associated with that mechanically forced orographic gravity wave. Here's the humidity anomaly associated with that gravity wave. And here's the x versus height plot of the temperature anomaly. And what you see is that there's a certain vertical wavelength of that gravity wave. And the theory, the linear gravity wave theory, tells you it's very simple. That wavelength is proportional to the cross-slope wind speed divided by n, the buoyancy frequency, or the Brute-Weisselot frequency. So as you increase your cross-slope wind speed, you expect this wavelength to change. And we can see that as we go from 10 to 12 meter per second cross-slope wind, indeed, that temperature anomaly and the humidity anomaly, they get deeper. Okay? And that would mean that averaged over this layer, you have a stronger negative temperature perturbation and little bit of feedback here with this reduction in humidity. But overall, you have an increase in the humidity.
Did you change this here? You did change.
We changed U in the theory. Yep. We put in two values, 10 or 12. If we're going from 10 to 12, you're going from the solid to the dashed curve. Yep. And the gravity wave is getting deeper. And so average over this layer, the average temperature anomaly over this lower tropospheric layer is getting more negative. Right? That would force stronger precipitation. And you just have to then ask, you take the change in the layer averaged anomalies due to that deepening of the gravity wave structure, and you just put it in that convective closure. And that gives you that 25% per Kelvin.
Mean deeper convection?
It's not deeper convection. So this convective closure actually says nothing about the vertical structure, right? This just says precipitation is proportional to these quantities. But we did, you can think about, for example, a humidity vertical structure. And you could think about like a first baroclinic mode temperature anomaly and some kind of standard humidity anomaly that would change and be your, when we had the humidity feeding back via the convection, there would that humidity feedback by the convection would have some kind of assumed vertical structure. This is all very simple.
Because the temperature cooling is extending vertically.
The cooling extends vertically. Sorry, say again.
Cooling, it gets adiabatically lifted and it cools. And that vertical extent is increasing, right? You increase the wind speed.
Yes.
So does it mean the vertical velocities are increasing?
The vertical velocities will change. And that also comes out of the linear gravity wave theory. If n is fixed and you increase U, you will indeed get faster vertical velocities, right? But one thing I want to emphasize here is that the main difference between what we're proposing here, the theory for orographic convective precipitation that we're proposing here, is that precipitation does not depend on the vertical motion. Classic mid-latitude, with classic mid-latitude theories, vertical motion gives you precipitation. Here, vertical motion modifies the temperature and humidity of the free troposphere via adiabatic cooling and vertical moisture advection. The temperature and humidity anomalies then act on the convection via the buoyancy of convective plumes. That's what modifies the activity of the convective ensemble, and that gives you the precipitation. So vertical motion only comes in via the gravity wave response. And that's, incidentally, that's why, here, if you had precipitation depend on vertical motion, you would get this downstream precipitation peak. But so you do actually have upward vertical motion here. But because the upward vertical motion is because of the accumulated warming and drying that has happened after the flow went over the mountain, that upward vertical motion doesn't produce convective precipitation. And that's what the theory gets right. Okay, so we can do the same experiment, not in the theory. It takes a lot more computing time and analysis, but we can do this in the cloud resolving model. And the convection permitting simulations also have a high sensitivity. A little messier. You have a lot of this. Here's precipitation, rain rates, millimeters per day for a fixed sea surface temperature of 300 Kelvin. This is a 1200 day average. And what you see is that here's your upstream precipitation peak. And this is a fairly warm SST. Here's precipitation anomaly. This is P prime. So note that it goes to 0 upstream in the mountain. So we've already subtracted off a background rain rate. That's why it looks wavier than what I showed you before, because we've subtracted off whatever the upstream background rain rate is. And then you see here is the rainfall enhancement above the background. That increases, the orographic rainfall enhancement increases by 24% for each meter per second change in the cross slope wind. We can take from the cloud resolving model the free tropospheric humidity and temperature anomalies and the theta E in the boundary layer, put them into our convective closure, and they give us about 18% per meter per second. 18, 24, somewhat different, but the error bars here shown in brackets overlap a fair amount. And so these two quantitative estimates aren't really different. They're both, I look at this and I say they're around 20% per meter per second. Observations also show a high sensitivity of precipitation to cross slope wind speed. We did the same exercise for cross slope winds across the Western Ghats using precipitation from quite a long time period, 1960 to 2015. We took wind, and this is wind from ERA 5 data, which now extends back to 1950. We took the cross slope wind, averaged it over this box, and then we took rain, averaged it over this Western Ghat region, and regressed precipitation at every point first, and then averaged, took the regression averaged over that region, and plotted as a bar down here. And what I'm showing you are 3 bars. Let's look at the Western Ghats first. If you just take the total observed seasonal precipitation, you get around 15% per meter per second change in cross slope wind. But remember, the theory tells us a P prime, how much precipitation is enhanced above a background, background oceanic non-perturbed rainfall state. So we actually did compute some averaged upstream rainfall, seasonal mean, subtracted it out, and then you get more of 25% per meter per second. We then did that not with seasonal mean, but over a much shorter time period, year, I think roughly 2000 to the present, 20 some years, and did daily precipitation anomalies, and then we're getting above a 30% per meter per second. We also did the mountains of Myanmar, Vietnam, the Philippines, and Malaysia. I think it's good to look at how the total precipitation changes, but that's not what the theory tells us about. The theory tells us about the orographic perturbation relative to the background. So that's where we have to subtract off a background state. And when we do that, the orographic perturbation scales in all of these different regions for seasonal mean or for daily by around, ballpark 20-some% per meter per second. So that's quite large. And I want to close by just putting up my summary. This is perhaps not as short as anticipated, but I guarantee you I only had 20 slides. But I have really 3 main takeaway points. One is a new theory for the convective response to gravity waves that are mechanically forced by the orography. that essentially gives us a new way of thinking about tropical orographic precipitation, the mechanically forced type. So don't think of, my argument, and this is new, so this is a proposal, but it's the argument is don't think about convective precipitation over orography due to flow going over the mountains as being produced only by the vertical motion. It's produced by the response of convective clouds to the temperature and humidity anomalies in the orographic gravity wave. That theory, it tells a number of things to us. It gives us the magnitude of the upstream rainfall enhancement, the length scale of the upstream enhancement, the length scale of the rain shadow, and it also gives us a sensitivity of that precipitation to changes in the cross-slope wind speed, and it tells us that is quite large. This is documented in 3 papers, all of which are available. One of them is still in review because these all came out of Clinton's thesis, and the most recent one is in review at Weather and Climate Dynamics, but there's a preprint online, and that's the sensitivity to wind speed one. So I'll end there and happy to take questions. Questions or discussion. I know there's a lot of people in the audience
discussions, yeah,
who work on orographic precipitation, and I would love to hear your thoughts, comments.
Yeah, we'll start with the
Thank you very much. That was a brilliant talk. This gravity waves, how much vertically, what would be the depth? How deep they extend in they go beyond the troposphere, even into the stratosphere and even above? So
they can, orographic, like this is, so, here's the cloud resolving model, right? So this is not the theory. The theory, what do you do with the stratosphere? That maybe isn't too relevant because that'll just be an answer you put in.
But some work from IAG, against of geometry. Thesis came to me for evaluation. So they've identified gravity waves triggered by Western Ghats precipitation. It even goes into the mesosphere.
Yes. Yeah.
That's what I was.
And it's the gravity waves not excited by the convection, but the gravity waves excited by the mountain. Is that what you're saying?
No, it is effective activity.
Oh, okay. So
they were reporting up to even the mesospheric levels.
Right. So, and that makes sense. There's a large community of people that work on orographic gravity wave drag, as well as gravity wave drag in general. Typically, this is in the upper atmosphere. This is stratosphere and higher, because the stratospheric circulation is heavily influenced by gravity waves propagating upward, and the density becomes very low, and the amplitude, because the density becomes low, the amplitude becomes very, very high. And so these cold and warm temperature anomalies can actually cause the flow to go convectively unstable, and then you have overturning and turbulence, and the waves break, right? You have your surf zone then up in the stratosphere. And so that can have, you have mid-latitude strong jet stream flowing over mountains in the middle, that can excite gravity waves that propagate up. But convective activity in the tropics can also excite gravity waves that propagate up. So I'd be curious if the Western Ghats are convectively excited or mechanically excited.
Maybe I can share those papers.
Yeah, that'd be cool. Yeah.
Both things. This is mostly you focused on the Western Ghats. How about the Myanmar? Have a similar result for Myanmar?
Well, I mean, I guess a lot of my motivation here was on the Western Ghats. The slides that I showed at the beginning, this is the Western Ghats right here. But this is just kind of motivation, right? There's nothing we're doing here. But the main thing at the end, the one thing where we actually used an analysis of the Western Ghats was this analysis, right? This observational analysis of what's the observed sensitivity of orographic precipitation to changes in cross-slope wind speed. And this figure is for the Western Ghats, but in the paper, there's a figure just like this for each of these other 4 regions. And so you can see a map like this for Myanmar, Vietnam, etc. Yeah.
And one last question, this, can you compare the British Columbia, high latitude?
Yep.
So there you use the convective feedback, is it? The one that you,
Oh,
the temperature,
you mean in this radar map of the,
not the previous one.
this right here? Or
Had those temperature anomaly and humidity anomaly feedback equation you had shown.
oh, okay, yes. This, okay.
So you say in the Western Ghat case, the temperature anomaly, you don't have the convective feedback.
Right.
So, and then in the case of the British Columbia,
Oh,
if you want to apply this, how will you deal with it?
so we would not apply this to British Columbia, because my argument would be that the British Columbia case is not convectively unstable. And so the classic mid-latitude theories for orographic precipitation are more appropriate to use there, because it's like layer-wise ascent and condensation. But this is appropriate to use when you have convective precipitation. So if you're, if you can look at radar data and see that your orographic precipitation looks like, an ensemble of convective clouds, as opposed to just some big stratiform layer in which condensation has occurred, then, for the ensemble of convective clouds, this is what we're arguing is appropriate.
Thank you.
Thank you, sir. So Anupam has a question. I'll come there. Can somebody pass them?
Hello. Yeah, it's a very nice talk. So I have a couple of questions. So first of all, the Western Ghat and the Myanmar coast. So the height of this topography almost same. So how do you feel that the rain mechanism is same for the two orography regions? Number one. Number two, that if we consider a theory that that how it affects on this dynamics. So can you explain the both rainfall through the dynamics only? And if we look into that central India, where there is a homogeneous region, how we can differentiate that topographical theory and that the homogeneous region, that rainfall mechanism? So how you can explain that? And third is the convective, you are explaining the convective closure. So whether the convective closure based on this theory of the orography can be applicable for everywhere.
So I won't be able to answer all of your questions, but I probably won't be able to remember all of your questions. So please remind me if I maybe let him keep the microphone, because I'll probably have to come back. But the first one was about how are the Western Ghats different from Myanmar? And we do have, at the end of my talk, I listed Quentin's these three papers that were relevant to the results that I showed you today. And in the second paper right here, we actually take the theory that I showed you the one-dimensional form for, and we actually take observed topography, and we extend the theory to 2 dimensions and create via just a two-dimensional Fourier transform of the topography. We create a gravity wave solution and then allow that to modify the convection via the same closure. And then you get a precipitation distribution. And so we do in that paper show, I think we answer that question. It would be hard for me to describe details of, like what is the result, but it looks, for a number of regions, we look at 6 orographic regions around the world, and it doesn't work perfectly for all of them. but I think it does a decent job for many of them.
Yeah. The total rainfall over the Western Ghat and Myanmar coast are same, but whether the rain mechanism is the same. So this was my first question.
So in that paper, we don't just look at the rainfall. We don't just compare observed rainfall to, we don't just look at the observed rainfall and compare it to the theory, but we say, okay, the theory predicts that you're getting that observed rainfall response because of a temperature anomaly, a humidity anomaly in the free troposphere. We look at the observations. We look at ERA 5 data, for example. We see, do you have a temperature and humidity anomalies that are consistent with that? Are they the right magnitude that would be consistent with that precipitation response? And indeed, you do see that. So I think there is, in that paper we do show there is a fair amount of support for the theory mechanistically, not just at the precip matches. Yeah.
Okay. And the convective closure you have mentioned. So whether the convective closure from this the orographical theory, so whether it will be applicable, it is a dynamical thing. So whether it will vary for all regions if we use the fixed convective closure.
So remember, this is a theoretical convective closure. This is, if you're familiar with the Betz-Miller scheme, right? The Betz-Miller scheme is, you could think of it as it's the conceptual basis for what goes into like a Arakawa-Schubert scheme for a climate model, but your climate model Arakawa-Schubert or your NWP parameterization would be a lot more complicated, but the theoretical model would be very simple and it would apply to, you would just use it generically, right? This closure that we used, that we took from this Ahmed and Neelan paper comes from, I mean, it's in many ways what they did was they encapsulated into just a very simple mathematical form a recognition that the tropical dynamics community has come to over the past 20 years, which is that convection responds very sensitively to temperature and humidity anomalies above the boundary layer in the lower free troposphere. I think of a paper by Derbysh in 2004 from the UK Met Office that showed how sensitive convection was to dry anomalies, around 700, 800 hectopascals.
So what is your suggestion that suppose if we go to the Jack-McFargan that convective closure or Arakawa-Schubert, so which will be the best for this topographical rainfall mechanism?
I mean, that's a great question. We have not taken this step. This is all new. You can see the dates of these papers, right? 2024 in review. The theory, we first laid out in 2022. But what is hopeful is that we're not proposing anything new about a convective closure. What we're saying is that your convective closure, your parameterization should be sensitive to temperature and humidity anomalies, should be appropriately sensitive to temperature and humidity anomalies in that lower free troposphere. And if you want to get orographic precipitation right, you need to get the gravity wave response to the orography correct. So, will your model have a horizontal resolution that is sufficient to do that? Well, if you're running a 12-kilometer horizontal grid spacing operational model, 12 kilometers might be decent. It would be nice to look at that model and see, do you see those gravity wave structures? I would imagine certainly if you increase it from 12 to 6 kilometers, that would work. If you're running at 50, 100 kilometer resolution, you're probably not going to resolve that gravity wave. And so, that's when I showed that slide from GCMs, I'm actually pessimistic that any of our CMIP models are even. I think that none of our CMIP models, I don't think we should be looking to them to answer the question of how tropical orographic precipitation will change as a result of climate change over the next 100 years. I just think, they have convection schemes, they have biases, but they're not resolving the gravity waves.
Okay, so one question by Dr. Sachin. I'll pass the mic. Can somebody say that?
Here, you can use my microphone.
In one slide, you explained about for the given background flow, how the precipitation maxima and the length of precipitation varies. But in the nighttime, when there is a downslope winds, so how does this precipitation maxima and the length of precipitation varies?
So remember that the theory that we're proposing is only for mechanically forced precipitation. So there needs to be a background constant, background nearly steady cross slope wind flow. So if you're talking about horizontal wind that goes across the mountain changing between daytime and nighttime.
Yeah, so nighttime there is a downslope wind, so definitely it will have some. So what's your thought on that?
My thought on that is that we have no idea, because that is in this thermally forced category right here on the right, and we're only talking about the mechanically forced category. So I have nothing to say about this.
Because there is an offshore maxima also along there are two precipitation maxima in the west coast, one along the parallel to the topography, and then there is an offshore maxima.
You're talking about the Himalayas?
No, in the west, in the Arabian Sea also.
The Western Ghats. But you're talking about diurnal modification. Yeah. So the Western Ghats, if there is a diurnal cycle, it's small. Right, the diurnal cycle of the Western Ghats rainfall is pretty small compared to the peak. My argument would be that take the diurnal mean, and what I laid out is going to be relevant to the diurnal mean, and it doesn't tell you anything about the diurnal fluctuations about the mean. Yeah. Maybe you could get something, but maybe not.
Okay. See, when your theory is very well fitting into this Western Ghats, whatever Anupam has asked, when it comes to Myanmar coast, the Arjun is much larger compared to Western Ghats, and winds are much weaker. So the theory will be completely different, and also SSTs are much warmer.
Yeah.
So the same theory, I doubt, may apply to Myanmar.
So in this 2024 paper that I showed at the end, we took the theory, we extended it from 1 dimension to 2 dimensions. In this 2024 paper, which was recently published in Journal of Climate, we took the theory, we extended it from 1 dimension to 2 dimensions, applied it to the Western Ghats, to Myanmar, to Papua New Guinea, New Britain, the Philippines, 1 or 2 other places. And we compare, and then for each region, we put in the observed upstream cross slope wind, some parameters that are relevant to the background precipitation rate and background humidity. And I would say across all the 6 regions, it works decently well. It's not perfect, right? We're not capturing every detail of the orographic, the precipitation profile around the orography. But I would direct you to that paper to look in detail at what's, I just don't have the slides here of every 6th region and how precipitation behaves around each mountain range on the planet. Yeah, but we have done that work. And, if you have a suspicion that it doesn't work, I would direct you to that paper, because which has been through peer review. So, yeah.
Siddharth.
So I've been a very excellent talk. So you have reported, when you look at the response of increase in wind speed to precipitation, you are saying that 20 to 30% per meter second change. But in this case, your base state is 10 meter per second. So does it apply to all the base state? Let's say your control run is 20 meter per second, and then you increase the wind speed by 1 meter per second. So will you get the same response, or is it only applicable to your control simulation 10 meter per second and increasing wind speed by 20% here?
We would really need to put that through the theory to find out. Great question. You can see that the response depends on how the gravity wave anomaly changes, temperature and humidity anomalies change within this layer that you're defining as the lower frequency over which convection is sensitive, right? So you can imagine that as your wind speed got very fast, this gravity wave would be quite deep. And then if you made it faster by 1 meter per second, it would deepen, but just by a little bit, right? And so you would need to do that. In the tropics, it's not that common that you have 20 meter per second cross slope wind speed, right? A steady wind speed. You might think of whether or not this could be applied to individual events. Do you have a tropical cyclone that is crossing, producing flow across orography? But I think we would need to go into that regime. We would need to see.
My second question, related question, is when you are running a WRF simulation and you are comparing with your idealized this framework, you are getting some difference. Like this is WRF simulation is showing around 18% increase in rainfall compared to your idealized 20-25%, right? So is this difference is coming because of the temperature response of convection is being accounted for in WRF simulation?
Sorry, you were saying this?
Yeah, this one, yeah.
Oh, the WRF simulation has no temperature change. I mean, the SST is...
No, I'm saying temperature response to convection. Is it counted in WRF simulation?
Oh, yes. I mean, I didn't really answer your question. But, the T prime anomaly is influenced by convection, but in the CRM, in the WRF model, it doesn't change that much. And so you can take the precipitation response that you would get to just the gravity wave anomaly and take the precipitation you would get the precipitation response you would get using this convective flow to the WRF anomaly. They're not that different. At a first order, you can neglect that temperature response. Does that make sense? Why these are different? I think that one thing I didn't tell you is that we're diagnosing all of these from the simulations. One thing that happens is in the cloud resolving model, the theta E changes, theta E of the boundary layer. And we do have an argument, it's a little bit involved. I won't go into it here, but we do argue that the gravity wave has an influence on theta E in the boundary layer also, because the gravity wave doesn't, the gravity wave can start right at the surface and it alters parcel motion below the base of convective clouds. So you can perturb theta E by the gravity wave also. And so my answer to your question is that convection does alter T prime, but I think that a bigger difference between the theory and the WRF model is what happens with theta E in the subcloud layer in the WRF model.
Yeah, thank you.
So anybody has question, quickly come forward. Yeah.
I really enjoyed your talk. So the vertical velocities you have shown in the windward side and leeward side. So there is a heterogeneity. Is it mainly due to the humidity and temperature fluctuations brought by the low-level jet? In the simulation, WRF simulation.
Yeah, it's mainly brought. Let's see.
Yeah, this one.
Okay, this. So these are vertical motion anomalies, and not temperature anomalies, but this would be a cold anomaly right here. You'd have a warm anomaly, but once you move past the mountain, the W and the T prime anomalies don't look identical. But you're correct, yeah, exactly. That the convective response is primarily due to the accumulated action of the vertical motion of the gravity wave on the temperature and humidity anomalies.
To the past two side, it is diminishing.
Yep, and so here you have a lot of convective activity. This is the windward side. Leeward side, the convection is shut down. And that's because in this layer right here, this is our argument that here the temperature of the lower free troposphere is cold, here it's very warm, and it stays very warm all downstream of the mountain. Yes. Yeah.
Even up to -300.
Yep, it stays, the warm anomaly extends quite far downstream of the mountain.
Good work.
Yeah. It's a really very nice talk, and even the precipitation in the form of the gravity wave and new perspective. It is very interesting to think on the gravity wave perspective. So just I have some clarification. See, like for the first thing is this. I'm thinking for the ideal case, it is fine. So when we have the gravity wave, it is directly it is doing the vertical propagation was very high enough. Then this I can understand. When about the kind of a trapped living condition, where is the mechanical forces being damped because of some sort of mechanisms. So in that case, any simulation you have experienced? I mean, what kind of precipitation response you have been in still that case? Because where you don't have a vertical propagation, where you have a horizontal propagation is much enough. So how this will be respond? This is one. And finally, second is that in the equations, we can see that theta E, it plays a major role. Like when you means you have kept constant for your buoyancy term, like in this stability is being treated as a stable conditions, I believe. So suppose if it is an unperturbed condition, if stability changes, suppose unperturbed, because we cannot expect the gravity for the season. Right. So throughout the season, we cannot expect the gravities over the orographic. So it may have a various phenomena. So how that will cause the precipitation changes? Thank you.
So we've only, the goal here was just to start simple and just say, okay, we want to understand how does tropical orographic mechanically forced precipitation work. So we started with that simple vertically propagating non-trapped gravity wave. If you do have some vertical shear, all of this is just constant horizontally uniform and vertically uniform cross slope flow. We don't have any kind of vertical shear in the cross slope wind that might, trap your gravity waves. I think you could put that in. It would be certainly interesting to see, if you do put that vertical shear over the Western Ghats and it changes your gravity wave structure. That would be interesting. One thing to keep in mind, though, is that remember that the convection is sensitive to the temperature and humidity anomalies in this layer. So if you're trapping your wave and what you're primarily doing is not allowing the wave to propagate up here, if you're not substantially changing the temperature and humidity anomalies in this layer, then it doesn't really matter. And so that's an interesting question. Yes. And I think worth working on is, how sensitive can you be to a shear in terms of your convection? How sensitive is your precipitation to the shear, given that your convection is only responding to what the gravity waves do in this lower layer? Your second question, I'm sorry, what was that?
Theta parameter, when we are stabilizing, you kept as a background as very stable for running this.
Yes, right. Thank you. The stability, yeah. So n squared in the tropics doesn't change a whole lot. The moist stability certainly changes. But if you think about n, 0.01 per second, pretty decent for the tropical free troposphere, pretty decent estimate. I mentioned that we have started working on the response to warming. I only showed you the response to dynamics. The response to warming, a key component of that is the change in n. The gravity wave vertical structure is changing, gravity wave wavelength, vertical wavelength is changing because it's proportional to u over n. We looked at the change in vertical wavelength due to the change in u. You can also think of the vertical wavelength changing because of the change in n. And so we have ongoing work, but it's not as simple of a story. The cloud resolving model simulations are a little harder to understand. And we think that it's possible that the convection may be interacting more with the gravity wave, perhaps, especially as you get to warmer, 304 Kelvin SSTs. So we're still working on that.
Yeah, it's very good that maybe for students to note that with this linear theory, they could arrive up to 25% accuracy. I mean, 75% above accounting the what models WRF is simulating with all processes involved. One quick question: what sets up this upstream length scale? It looks like you don't have any rotation here. So what sets up the upstream length scale? Is it the topography, the slope term brings this length scale?
Oh, you mean why is precipitation enhanced so far upstream?
Yeah. I mean that length scale, the decaying length scale that you mentioned that in the beginning, but there was no discussion of that. What sets up that length scale? So these are free gravity with no rotation. N square is governing the dynamics.
Yep. So you're right that in the theory there's this length scale, right, that you can think of as going the wrong direction.
I think in the beginning you showed that.
Yep. In the theory, you can think of the length scale as a decay scale.
Okay.
Like this is a single variable ODE, right?
So they have exponential solutions, maybe.
Yes.
And no deformation radius coming into picture, because you mentioned that word in the beginning. That's what I was curious.
But if you look at the gravity wave response, so this is a linear gravity wave solution to this mountain shape.
Okay.
And so look at what happens upstream, right? We kind of think of this gravity wave has this tilted structure, but look downstream, the displacement. This is not vertical motion. This is displacement. Like think of this as your isentropes. As the adiabatic flow goes up or the mountain, they're perturbed up and they're perturbed down, right? Mm-hmm. And so upstream and downstream, there's a pretty large displacement. This would be a warm anomaly. This would be a cold anomaly. And your cold anomaly, due to the linear gravity wave, extends hundreds of kilometers upstream of the mountain. And so that's the argument, is that upstream of mountain ranges, you're perturbing the buoyancy of convective plumes by altering the temperature of the free troposphere by gravity waves.
Okay, thank you. So I think we'll give a big round of applause for... And we have a small memento from IITM. So I invite director to...
And maybe if I could just say one more thing.
Yes, sure, please.
Which is that I would just like to again acknowledge that this is work, what I talked to you about was work that was done by Quentin Nicholas in his PhD thesis. And, I just think it's great when I usually when I'm in the US, I won't talk about this because that's his job. But it might be a long time before he makes it to India to talk to you all. So I wanted to share this with you, but I just think it's important to see the good work that our students do. And to see that, as a PhD student, you can make important contributions to our understanding of the world around us. So thanks. Thanks to Quentin. Beautiful. Oh, wow. Nice. That's beautiful. Thank you. This is very nice.
Thank you, everyone.